Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the strange, beautiful foundations of everything, into the quantum roots of reality itself. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always a joy to see all the places we gather from, a constellation of minds, each in its own little pocket of time. Now feel free to dim the lights, maybe let the room grow just quiet enough that you can hear the hum of your own breathing. The day can wait outside the door for a while. Tonight we're going to follow a very small idea, a single spark of thought that ended up changing our understanding of the entire universe. Imagine a room at the dawn of the 20th century. Gas lamps flicker, notebooks lie open, and somewhere, a quiet man in Berlin stares at numbers that refuse to behave. He's trying to describe how light glows from a heated object. A black piece of metal, perhaps, burning orange, then white. The math should have been simple. But as he followed the equations, they exploded into infinity. Every colour, every frequency seemed to pour out boundless energy. It was nonsense, but it was the kind of nonsense that hides a secret. His name was Max Planck, and in 1900 he took a step that he later called an act of desperation. To make the numbers behave, he imagined that light didn't radiate continuously, but in tiny jumps, little packets of energy, each tied to its colour. The higher the colour's frequency, the larger the packet. In the softest possible way, the world had just become pixelated. Planck didn't think of himself as a revolutionary. He only wanted to fix an equation, not rewrite reality. But with one quiet insight, he introduced something that no one had seen before. The idea that nature comes in quanta. A quantum, he called it. The smallest piece of energy that cannot be divided further. If you could listen closely enough to a beam of light, it wouldn't hum in a smooth note, but in a rapid tremor of tiny discrete beats, each one carrying a fixed amount of energy, the same way every heartbeat carries a pulse. Energy, Planck said, rises in exact proportion to frequency. The faster the vibration, the higher the step. He even gave the world a constant of nature to express it, a simple number that would come to haunt and illuminate all of modern physics. We now call it Planck's constant. It's small, unimaginably small, but it anchors everything from the glow of a candle to the creation of stars. For Planck, it was a mathematical trick. He didn't imagine that reality itself might be grainy. But within a few years, others began to see that this wasn't just math, it was the world whispering its true nature. You can almost picture that moment in history like the first crack of dawn over a calm sea, the classical world of Newton and Maxwell beginning to shimmer as something stranger and finer stirred underneath. If we follow the thread a little further, we meet a young man who would take Planck's hesitant idea and turn it into something daring. His name was Albert Einstein, and he was working at a patent office in Switzerland, a place filled with ticking clocks and paperwork, the hum of precision and boredom. But in that quiet, Einstein began thinking about light again. When light shines on a metal surface, it can knock out electrons, a small but definite current. Classical theory said brighter light should always eject more energy, but experiments refused to agree. Only the colour, the frequency mattered. The bluer the light, the stronger the kick. Einstein realised what Planck's numbers were really saying. Light itself must come in quanta, individual particles of energy, each like a tiny bullet of brightness. He called them photons. It's a lovely irony that one of the calmest minds in physics opened the door to one of the wildest ideas, that light can act both as a wave and as a particle, depending on how you look at it. Sometimes it spreads and interferes like ripples across a pond, Other times it hits with the certainty of a pebble. The universe, it seemed, refused to choose. It was as if nature had decided that being two things at once was simply more elegant. The birth of quantum theory didn't begin with lasers or atoms in boxes. It began with colours, warmth, and curiosity, with human senses trying to make sense of glowing metal. And yet hidden in that familiar glow was a doorway into a world that would soon make intuition tremble. It's worth pausing to notice the gentleness of it all. The greatest revolutions in science often start not with thunder, but with a quiet mismatch between expectation and reality. A line that doesn't add up, a colour that burns too brightly, a scientist too stubborn to look away. As we drift further into the story, we'll see how these small packets of energy, these quanta, begin to reshape everything we know, how they form the structure of matter, how they blur the boundary between certainty and chance, and how, from their dance, the very fabric of space and time begins to emerge. But for now, you can imagine that first moment in Planck's study, the air heavy with lamplight, the equations still warm on paper, and the faint realization that somewhere, in those tiny jumps of energy, the roots of all reality were quietly taking hold. When the morning sun hits a metal surface, a quiet miracle unfolds. Electrons leap free, as if startled awake. To most people it's invisible, but to physicists in the early 1900s it was a riddle. They called it the photoelectric effect. When light shines on metal, it can kick out tiny charged particles, creating a current. The mystery was that the brightness of the light didn't matter. You could pour on more and more light, flood it with brilliance, and yet if the colour was too red, nothing happened. Only light above a certain shade, a certain frequency, could free the electrons. It was as if the metal cared not about how much light arrived, but about the energy carried by each individual ray. Einstein looked at this puzzle and saw something deeply simple. He took Planck's trembling idea that energy comes in packets and gave it a heartbeat. He proposed that light itself is made of individual quanta, particles of pure energy. Each one carries an amount of energy tied to its colour, just as Planck had found. The bluer the light, the higher its energy, the redder, the gentler. Each photon, as he called it, behaves like a messenger. It can strike an atom, give up its energy and vanish, leaving behind a freed electron. In this view, brightness is merely the number of messengers, not their strength. It was a small shift of language, but an immense shift of reality. Until that moment, light had always been treated as a wave, a vibration travelling through space. Waves explain reflection, refraction, interference, everything elegant about light. But Einstein dared to say that, under certain conditions, light behaves like a stream of particles. Not metaphorically, not approximately, actually. The universe, it seemed, could wear two faces. Sometimes it rippled, sometimes it rained. Imagine the shock. For centuries, scientists had fought over what light truly was, a wave or a particle. Newton had championed particles, Maxwell had crowned waves. Now Einstein suggested it was both. He didn't mean that light changes its nature depending on our whim. Rather, that both pictures were incomplete, and nature, as always, refused to fit neatly into our words. The truth was subtler, more musical, like hearing a note that is both clear and echoing at the same time. Einstein's insight didn't just explain the photoelectric effect, it opened the gates to the atomic world. If light could be quantized, then perhaps everything could. The solid world we touch, the heat we feel, even the atoms inside us, all might share this same rhythm of discreteness. The classical illusion of smoothness began to dissolve. In its place appeared a cosmos made of steps so small that, from afar, they looked like continuity, the way individual waves blend into the calm of a sea. The photoelectric effect may sound abstract, but it's woven quietly into our everyday life. Every solar panel, every camera sensor, every automatic door that opens when light touches a detector, all are children of Einstein's idea. When sunlight strikes a silicon cell, electrons leap free and create current. It's the same dance that puzzled scientists a century ago, now harnessed to power homes and satellites. A reminder that even the strangest theoretical insights eventually find their way into our mornings. There's something almost poetic in how light behaves. The same ray that warms your skin can also knock an electron loose. The same photon that makes a leaf shimmer with green is capable of freeing particles in a vacuum tube. It's a dance of gentleness and precision. And what's more, it teaches us humility. Nature doesn't answer in absolutes. Wave or particle, yes or no, but in both and neither. The universe prefers paradox. It asks us to hold two truths at once and see them not as contradictions but as complementary melodies. Einstein's paper on the photoelectric effect was published in 1905, the same year he wrote about relativity. But it was this quieter work, not the speed of light or the bending of time, that would one day earn him the Nobel Prize. The world noticed that behind this mild-mannered patent clerk was someone who saw simplicity where others saw confusion. And maybe that's what quantum physics really is, a language for the universe's simplicity, one that just happens to sound strange to our ears. If you step outside at dawn, when the first light catches dew on grass or glints off a railing, you can almost picture what Einstein imagined. Each tiny sparkle isn't continuous illumination, but a rapid storm of invisible grains, each one carrying a discrete packet of energy. You don't need to see them to feel their rhythm. They're the reason warmth spreads, shadows soften, colours bloom. Every glint of sunlight is the universe's quiet confession that reality is built from little bursts of something indivisible. From here, the story opens into an even deeper mystery. If light behaves like particles, what happens when we let those particles pass through the same narrow doorway? A slit so thin that a wave would spread, but a particle should simply pass or not. What happens when we test whether light's duality is a trick of our perspective or a law of the cosmos itself? The next step in our journey will take us to that thin barrier, to a simple, elegant experiment that reveals how the universe decides what to show us and when. There's a certain charm in experiments that look simple enough to fit on a kitchen table, but end up unravelling the nature of existence. The double-slit experiment is one of those quiet riddles. You could almost imagine performing it yourself late at night, with a dim lamp and two thin openings cut into a piece of cardboard. Light passes through the slits and lands on a screen behind them. What should happen seems obvious. Two bright lines matching the two slits. But that's not what appears. Instead, you see a pattern of bright and dark bands rippling like gentle waves meeting and parting on a pond. Where one wave crest meets another, they amplify each other. Where a crest meets a trough, they cancel, leaving darkness. The pattern is unmistakably wave-like, the signature of interference. The light, it seems, has passed through both slits at once, like a ghost that refuses to pick a side. For centuries, this was enough to prove that light was a wave. But then came a new twist. In the 20th century, scientists decided to slow things down, to send particles one at a time. Not light, but electrons, each tiny as a whisper. You'd think the result would change. After all, how could one particle interfere with itself? And yet, after many electrons had passed, the same pattern slowly appeared. The same delicate stripes of brightness and shadow. Even when the particles travelled alone, never meeting one another, they behaved as if they each took both paths simultaneously and then interfered with themselves. It was as if reality were performing a quiet magic trick behind our backs. To test this, physicists added detectors, little devices to check which slit each particle went through. Suddenly, the interference vanished. The pattern dissolved into two simple bands, just as you'd expect from classical particles. The act of measuring, of trying to know which path the particle took, forced it to choose. The mere possibility of knowledge changed what nature showed us. When we looked, the universe behaved like matter. When we looked away, it behaved like a wave. It's difficult to overstate how strange this is. The outcome depends not on the particles themselves, but on the information available to the observer. If you erase the information, even after the particle has passed through, the interference returns, as though the universe politely rewinds its behaviour once our curiosity is removed. In the so-called delayed choice, or quantum eraser versions of the experiment, physicists play with time itself, deciding after the fact whether to preserve or erase which path knowledge. And the universe obliges, rearranging the results as though it already knew what we were going to ask. It's not that the future changes the past, but that the distinction between them becomes softer, less absolute. To make sense of this, we often reach for analogies. Imagine tossing two pebbles into a calm pond and watching the ripples overlap. That's the wave picture. Now imagine throwing single grains of sand one after another, each leaving a mark where it lands. That's the particle picture. In the quantum world, both happen at once. Each grain behaves like a wave of probability, spreading out and exploring all paths, both slits, all possibilities. But when we finally observe it, the wave collapses into one specific outcome, a single spot on the screen. It's as though reality keeps its options open until someone asks the question. Some physicists describe this as a superposition of states. That phrase can sound cold and mathematical, but it simply means that until measured, a system exists in many potential forms at once. Much like a melody waiting to be played, the measurement doesn't merely reveal a property, it brings one into being. The moment of observation is like the pluck of a string that transforms silence into sound. When you think about it in everyday terms, the idea feels impossible. How can something be in two places at once? But the truth is, that impossibility is built into the fabric of our world. Every atom in your body has existed in such shimmering states of possibility and continues to do so. They just blur together in ways that make our macroscopic world feel steady. The strange, flickering duality of quantum behaviour doesn't vanish. It merely averages out like the individual ripples of a storm that from a distance look like a single calm sea. What's most haunting about the double-slit experiment is not the apparatus or the mathematics. It's what it seems to say about knowledge itself. Reality doesn't unfold as a fixed story waiting to be read. It's more like a conversation. The universe offers possibilities, and the act of observation chooses one of them to speak into being. There's no trick, no conscious intent, just a deep relationship between what can be known and what can occur. It's as if the universe keeps one eye open to our curiosity, always aware of the questions we're capable of asking. If you imagine standing before that glowing screen, watching those bright and dark fringes appear, you might feel the same quiet awe as the first scientists who saw them. It's not chaos you're seeing, but something more tender. Order woven through uncertainty, a pattern that hides and reveals itself depending on your gaze. The faint shimmer of light and shadow is the universe whispering, I am not solid, not singular, not separate from your knowing. I am possibilities waiting for you to look. As we drift further into the story, the questions deepen. If a single particle can explore many paths at once, what about systems of 2, or 10, or 1 billion? How far can this fragile duality stretch before it dissolves into the classical world we recognize? Somewhere between the invisible and the tangible lies a quiet bridge, a way the quantum world becomes the ordinary one. And if we follow the thread of that bridge, we find a concept that gently explains why our tables, our trees, and our thoughts don't shimmer into uncertainty every time we blink. That story waits just ahead, in the soft place where chaos begins to settle into order. If we follow the thread a little further, we find that the story of quantum mechanics is not only about uncertainty, but also about how the world gently recovers from it. For all the strangeness we've encountered, like behaving like particles, electrons exploring multiple paths, the everyday world around us feels solid and reliable. Tables don't flicker between possibilities, and your cup of tea doesn't vanish into a cloud of probability every time you look away. Something, somewhere, must steady the quantum shimmer into the quiet certainty of daily life. That something is called decoherence, a word that may sound technical, but it describes one of the most graceful processes in nature, the fading of quantum possibility into the calm we call reality. To imagine decoherence, think of a coin spinning in the air. While it spins, it is neither heads nor tails, it's both at once, a blur of potential outcomes. That's what physicists mean by a superposition, a system existing in multiple states simultaneously. The moment it lands, it chooses. In our macroscopic world, that choice happens fast, almost instantly, because the environment is always watching. Air molecules, light, heat, even the faint vibration of nearby atoms constantly brush against everything, carrying away traces of information about what's happening. The result is that the quantum coin stops spinning almost as soon as it's tossed. The possible outcomes blur into one definitive result, not because the coin decided, but because the universe did. The idea that our surroundings are the great observer may sound mystical, but it's profoundly physical. Every interaction, every photon bouncing off a surface, every molecule colliding, carries tiny bits of information. Those bits accumulate like dust settling on a polished surface, covering the delicate quantum superpositions that once shimmered there. You can think of it as the fog of the environment slowly lifting, revealing one stable landscape beneath. The system doesn't collapse because of our eyes or our consciousness. It settles because it can't remain isolated. The universe itself, vast and restless, insists on clarity. When scientists like Wojciech Zurek began to describe this process in the late 20th century, it was as if the final missing piece had clicked into place. Decoherence doesn't remove the mystery of the quantum world, but it explains why that mystery hides so well. It tells us why the microscopic and the macroscopic don't behave in the same way, and why the strangeness of particles doesn't spill over into the solidity of stones. It's not that the weirdness ends at some scale, it's that the connections become too numerous, the information too diffused, for us to see the interference anymore. The music of quantum coherence fades into the gentle hum of classical reality. To bring the idea closer to home, imagine a choir humming in perfect harmony. Every voice corresponds to a different quantum state, all singing in delicate alignment. That's coherence, a state of exquisite order where possibilities overlap and interfere beautifully. Now, imagine a gust of wind blowing through the hall, scattering their sheets of music. The singers fall out of sync. The harmony breaks down, replaced by a soft, blended sound. That's decoherence, not destruction, but dilution. The song of pure quantum unity becomes the murmur of the everyday. Superposition and decoherence are like the inhaling and exhaling of reality. One brings forth a world of endless potential. The other restores it to the single world we inhabit. Every atom, every electron in your body once lived in a symphony of possibilities. They've since become entangled with countless others, the air, the light, the warmth around you, until their individuality fades into a chorus so vast it feels still. That stillness is the comfort of classical reality, but hidden inside it is the quiet trace of everything it once could have been. We can also think of decoherence as a kind of cosmic averaging. Imagine watching waves on the surface of an ocean from a high cliff. Up close, each ripple is alive with interference and pattern. That's the quantum view. But from afar, the sea appears calm, unified, predictable. The details have been washed out, not because they're gone, but because they've mingled together. Our world is that ocean seen from above, smooth and steady, yet built on constant motion beneath. Spin, another subtle quantum property, offers a beautiful example of this balance. Every electron has an intrinsic spin, an orientation that can be thought of as either up or down. But in truth, it can also exist in a superposition of both, like a compass needle vibrating between north and south. When left undisturbed, the electron holds both possibilities. The instant it interacts with the environment, one orientation becomes definite. It's as though the universe asks each particle, softly but firmly, "Which way will you turn?" And the particle answers with a whisper that decides an entire outcome. That whisper scales upward through everything. Atoms, molecules, entire structures. Decoherence ensures that once enough particles sing the same note, the world becomes classical again. Chairs stay chairs, stars stay stars. Yet the quantum roots never vanish. They're still there, pulsing quietly under the surface, like the unseen rhythm beneath a melody. There's a strange comfort in knowing that every ordinary thing around us, every coffee cup, tree leaf and book spine, is built on that flickering foundation of uncertainty. The order we experience is not separate from chaos, but grown from it, like a forest rising from fertile soil. The unpredictability of the micro-world gives birth to the predictability of the macro one. The fog settles, but it was the fog that made the landscape possible in the first place. If you pause for a moment and listen, really listen, you might sense it. The hum of countless interactions, photons striking your skin, air vibrating with hidden collisions. It's all information, softly exchanged, creating the quiet illusion of stillness that we call now. Reality isn't fixed, it's continuously resolving itself, over and over in every fraction of a second. From here, the story begins to widen. If a single particle can hold multiple possibilities, and the environment decides which one unfolds, what happens when two particles become linked? Their fates intertwined across space and time. What if their choices are not merely local, but shared? Our quiet exploration now turns toward the phenomenon that Einstein once called spooky action at a distance, a phrase half skeptical, half astonished. It is here, in the strange companionship of particles separated by light years, that the quantum world truly begins to stretch our imagination. When two people share a moment so vivid that distance never quite breaks it, we sometimes say they're connected, that a thread remains, invisible but real. In the quantum world, such threads aren't just poetic, they are literal. This strange link is called entanglement, and it ties particles together so deeply that even when separated by galaxies, they behave as though they are still one. To picture it, imagine a pair of twins born from the same cosmic event. You send one to a star system 1,000 light years away and keep the other here on Earth. Each twin carries half of a shared secret, not a message, but a pattern. When one turns left, the other instantly turns right, no matter the distance. Nothing travels between them, no signal, no whisper. Yet their actions remain perfectly correlated, as if space itself forgot to stand between them. This idea first appeared in 1935, when Einstein, Podolsky and Rosen wrote a paper asking whether quantum theory could truly be complete. Einstein was unsettled by the suggestion that reality might depend on chance, or on what we choose to measure. He called such invisible influence spooky action at a distance. To him, something had to be missing, some hidden variable that predetermined the outcomes. Nature, he believed, must still be playing by local rules, where causes have to travel through space step by step, like ripples spreading from a stone dropped into a pond. Decades later, a gentle but decisive experiment changed the story. The physicist John Bell proposed a way to test whether those hidden variables could exist. He showed that if local realism, the idea that properties are fixed and that nothing acts faster than light, were true, then certain statistical patterns would always hold. But if quantum mechanics were right, those patterns could be violated. The universe, in short, could choose correlation over locality. In the 1980s, Alain Aspect in France performed the first clear test. He used entangled photons, twins of light, and measured their polarizations with detectors placed far apart. The results broke Bell's limits. The correlations were stronger than any classical rule would allow. In the following decades, Anton Zeilinger and many others refined the tests, closing every loophole one by one. They sent entangled particles across entire islands, through optical fibers, even between ground stations and orbiting satellites. The outcome was always the same. Nature plays by quantum rules. The twins remain linked, not through a signal that travels, but through a shared wave of information that never fully separates. It's tempting to think of this as communication faster than light, but that's not what's happening. Entanglement doesn't let us send messages, it only preserves relationships. When you measure one particle, you instantly know something about the other, but you cannot control what that outcome will be. It's not telepathy, it's harmony. The two are like dancers who long ago learned the same choreography. When one raises a hand, the other's movement makes sense, not because they exchanged a cue, but because they've always been part of the same dance. There's an almost tender symmetry in that idea. The universe seems to prefer unity over separation. Even when distance stretches to cosmic scales, information can remain shared. Physicists describe entanglement as the fabric of reality because it acts less like a signal between points and more like a single field rippling in unison. The particles are not connected through space. They are the same phenomenon, extended across space. You can think of it like a drum stretched tightly across the cosmos. Tap one edge, and the vibration appears everywhere at once. Not because something travelled across, but because it was always one instrument. Entanglement tells us that particles aren't tiny billiard balls bouncing around. They're notes in a continuous symphony. Space, time, and separation are just the stage on which that music plays. And yet, this unity isn't reserved for physics alone. The same mathematics that describe entanglement also describe information, correlation, and coherence, words that belong as much to thought as to matter. In a quiet way, entanglement reminds us that knowledge itself is relational. We only understand something by how it interacts with something else, by how patterns echo between places. It's humbling to realize that at a fundamental level, the cosmos is a web of relationships. Every particle is connected to others through shared histories, common origins, and mutual interactions. What we call individuality is just a temporary boundary drawn around a cluster of correlations. Beneath it all, reality hums as one continuous whole, trembling gently at different points. When you look at the night sky, filled with stars scattered across the dark, it's easy to see distance and emptiness. But quantum mechanics hints at something softer, that every photon reaching your eyes has travelled not through nothingness, but through a connected medium, a vast field that once held everything in close embrace. Perhaps separation is an illusion of scale. Perhaps the universe never truly lets go. Entanglement isn't just a curiosity of subatomic experiments. It's the quiet logic behind technologies now emerging. Quantum communication, cryptography, teleportation of information. We've begun to weave this invisible thread intentionally, to use it as a channel for trust across distance. Each step in that direction brings us closer to seeing how unity can be not only a concept, but a tool. If you imagine two entangled photons floating apart, picture them not as travellers leaving home, but as reflections remaining in one mirror. They don't signal each other, they complete each other. Somewhere between them, the universe keeps the balance. As we drift deeper into this web of relationships, another question appears. If each pair of entangled particles forms a shared state, what happens when we begin to scale up? From 2 particles to dozens to hundreds, to systems so complex that no classical mind could ever track them all. That is where the idea of quantum information truly begins to unfold. Our next step takes us into that vast ocean of possibility, where every added particle doubles the universe's song, and where understanding means learning to listen to an exponential choir. If we follow the thread of entanglement a little further, we arrive at a sea so wide that no human mind can ever map it completely. The sea of quantum possibility. Each particle, each faint vibration of energy, can exist in multiple potential states at once. When 2 particles are linked, their combined possibilities multiply. Add a third and the combinations grow again. Add a fourth, a fifth, 1,000. And soon the space of potential realities expands faster than any ocean we've ever imagined. It's as if every new drop of water in that sea creates an entirely new dimension in which to swim. To picture this, imagine a simple compass that can point north or south. That's a classical bit of information, a choice between 2 options. Now imagine a quantum compass, one that can point to both north and south simultaneously, or to any direction in between. This quantum compass is what physicists call a qubit, short for quantum bit. It doesn't hold a simple yes or no. It holds a delicate balance of maybes, an overlap of all possibilities until someone looks. And when you link several of these qubits together, their collective potential doesn't merely add up, it explodes. 2 qubits can hold 4 potential combinations. 3 qubits can hold 8. With each new qubit, the number of possible patterns doubles again. 10 qubits can represent over 1,000 intertwined outcomes. 20 can represent more combinations than there are stars in our galaxy. This space of all possible quantum states is called Hilbert space, but it's easier to think of it as a vast library where each book represents one version of reality. Every time you add a qubit, you double the number of books, shelves, and entire wings. A classical computer could never walk through that library. It would take longer than the age of the universe to read, even a fraction of the shelves. But the quantum world doesn't need to walk. It exists in all aisles at once. It's as if reality reads every book simultaneously, letting interference between stories reveal the answer to a question we've asked. This idea is both thrilling and humbling. Thrilling because it means there is a form of computation built into the universe that is unimaginably powerful. Humbling because we realize that we can only glimpse it in tiny fragments through careful experiments and algorithms that feel more like poetry than machinery. When scientists speak about quantum computers, they aren't describing faster versions of the devices on our desks. They're describing machines that follow a completely different rhythm, devices that calculate by exploring entire landscapes of probability and then collapsing that landscape into a single meaningful answer. To make sense of this, imagine being asked to find one marked pebble on a vast beach. A classical computer would inspect each grain of sand one by one, counting until it finds the right one. A quantum computer, in its ideal form, would let the entire beach shimmer in superposition, every grain both checked and unchecked, every possibility alive at once. When the computation ends, interference between all those states ensures that the marked pebble, the correct answer, stands out. The rest cancel one another, fading away like the hum after a chord resolves. What took a classical mind an eternity becomes for the quantum world a single harmonic moment. Of course, the reality of building such machines is less poetic. Quantum states are fragile. The slightest disturbance can make them collapse. The qubits must be cooled to near absolute zero, shielded from stray light, vibration, or heat. Even then, the faintest touch of the environment introduces noise, the same kind of decoherence we spoke of earlier. The task of quantum engineers is to create silence in which the universe can whisper its calculations. It's a delicate conversation with nature, and every advance is a step toward hearing more clearly. But even if we never reach perfect quantum computers, the idea itself has changed how we think about knowledge. It teaches us that information isn't something we simply store, it's something we shape from the fabric of possibility. When we perform a quantum computation, we're not forcing the world to obey our logic. We're inviting it to explore its own natural harmonies and return an answer that already existed within its structure. In a way, we are collaborating with the universe, letting it solve a problem in the language it was written. There's something profoundly philosophical about that. The exponential explosion of states isn't just a challenge for technology. It's a reflection of how deeply reality resists simplification. Every particle, every molecule, every thought might carry connections branching outward into countless potential relationships. Complexity isn't a flaw, it's the essence of creation. Each time you add one more link, one more choice, one more voice to a system, the whole expands beyond measure. The same rule that governs qubits may well apply to everything that grows: societies, ecosystems, consciousness itself. Diversity multiplies possibility. When you look up at the night sky, remember that every photon reaching you is a messenger from that same ocean of potential. Each star's light could have travelled through countless quantum histories before arriving in your eye. Yet somehow, it arrives precisely, allowing you to see the shape of the universe as though it had always meant to show it to you. Perhaps that's what the quantum world is whispering, that from infinite possibility, order can still emerge. Patterns can rise from the swell, as songs rise from waves. And just as we are learning to build small devices that harness these probabilities, the universe has been doing it effortlessly for billions of years. Every atom, every chemical bond, every spark of life operates on principles that mirror quantum logic. Our own minds, the neurons firing, the memories forming, are built upon matter that still carries those ancient superpositions. In that sense, the boundary between physics and thought grows thin. To think is to explore possibilities. To compute is to let them interfere. As we move onward, the story becomes even more intricate. If each qubit is a compass in many directions, then linking them is like choreographing an enormous dance. A pattern of movements where one step changes the entire rhythm. Quantum computing is not just about states, but about transitions, about how probabilities merge and separate in time. In that dance lie the principles of quantum logic, the soft choreography of shadows and echoes that can transform uncertainty into knowledge. And that, quietly waiting ahead, is where our journey now turns. If we follow the rhythm of that quantum dance a little longer, we begin to see that computation, at its heart, isn't about circuits or numbers at all. It's about patterns of possibility, waves that merge and cancel, whispering toward an answer. In the quiet halls of quantum computing, logic isn't written in black and white, but in gradients of probability, as soft and overlapping as mist. Where a classical machine moves step by step, flipping switches between yes and no, a quantum computer moves like a dancer through a field of shadows, tracing every path at once, and then letting them interfere until only the right one remains illuminated. Imagine you're watching a ballroom from above, lights dim, music low. Every dancer represents a qubit, each holding countless potential moves, spins, turns, gestures. Some pairs move together, bound by entanglement, their rhythms perfectly mirrored. Others drift apart only to find one another again in time. Each motion affects the next, and as the dance continues, every possible configuration of the floor exists for a moment. Then, as the music slows, interference begins. Patterns overlap, some steps reinforcing, others cancelling out, until all that remains is a single, harmonious conclusion. The answer the computation was seeking all along. That's what a quantum algorithm really is. Choreography performed in the dark, where the measure of beauty is how perfectly the final motion reveals the hidden structure of the song. To make this possible, physicists build what they call quantum logic gates, simple operations that change the states of qubits. But unlike the rigid gates of classical circuits, these are transformations in phase and amplitude, rotations through the invisible geometry of possibility. You can think of them as subtle nudges, turning one wave slightly so that when it meets another, the peaks and valleys either reinforce or erase each other. The computation is less a march of commands and more a series of resonances, like striking a sequence of tuning forks and waiting for the note that lingers the longest. In this strange kind of logic, information behaves like sound. Two tones can combine to form silence, or to create harmony. Similarly, two quantum states can meet and cancel, or join to amplify the likelihood of an answer. What emerges at the end isn't a line of code, but a melody, a pattern of probabilities collapsing into a single tangible result. The universe seems to prefer that kind of language, one that flows, echoes and resolves, rather than one that dictates. There's a gentle but profound idea hidden here. Thinking, in the physical sense, always costs energy. Every calculation, every erased bit of memory leaves a tiny trace of heat in the world. This was first recognised long before anyone dreamed of quantum computers. The physicist Rolf Landauer showed that erasing one bit of information requires a minimum energy, not as a metaphor, but as a law of nature. You could think of it as the smallest sigh a system can make when it forgets. Each time a machine clears its memory, it releases that faint whisper of warmth into its surroundings. Even thought in its mechanical form is never entirely silent, but quantum computation offers a way to think that's gentler, almost reversible. If you could design a process where no information is lost, where each step could, in principle, be undone, then the cost of forgetting disappears. The computation becomes a graceful dance that leaves the floor untouched. No heat, no waste. This idea of reversible computation feels less like engineering and more like meditation, movement without friction, awareness without loss. It suggests that efficiency, in its purest form, isn't about doing things faster, but about not disturbing the universe as you do them. In that sense, building a quantum computer is like trying to choreograph silence, a silence so perfect that you can hear the smallest note of creation inside it. Each qubit must be shielded from the noise of the world, suspended at temperatures near absolute zero, where atoms barely move. There, in that cold stillness, the fabric of probability becomes soft enough to shape. When scientists manipulate these qubits, they aren't pushing electrons or forcing currents. They're guiding wave functions, coaxing the invisible geometry of reality into a form that aligns with our question. It's delicate work, more like playing an instrument than programming a machine. And when the answer finally emerges, it doesn't come as a sequence of numbers tumbling out of a printer. It appears as a single outcome in a sea of possibilities, a whisper rising above background noise. The machine doesn't choose the result any more than the universe chooses where a ripple will meet another. It's all written in the interference, in the overlapping of what could be with what is. Every time a quantum computer finds an answer, it's as if nature itself had participated in the reasoning, guiding the outcome through its own internal harmonies. This brings us to a deeper reflection. Perhaps intelligence, in any form, biological or artificial, is nothing more than the universe discovering patterns in itself. A human brain, a quantum circuit, a swirl of atoms in a cloud. Each is a configuration that allows the cosmos to notice something about its own structure. When we say a computer thinks, what we really mean is that it resonates. It creates interference between possibilities until a shape appears. When we say we understand, we do much the same. It's humbling to realize that every act of understanding, every spark of insight, is accompanied by a faint ripple of energy, a whisper of warmth to the world around us. Thinking is not abstract, it's physical, grounded in the exchange of energy and the movement of matter. In that sense, cognition isn't separate from nature, it is nature continuing its endless habit of folding complexity into awareness. If you were to stand beside one of today's quantum computers, a tall silver cylinder hanging quietly in its vacuum chamber, you'd notice the paradox. It hums with thousands of wires, cryogenic tubes and sensors, yet inside the real computation happens in near silence, in a handful of qubits suspended in the dark. Those qubits perform their invisible dance, then return to stillness, leaving behind only traces of probability measured and recorded. It's a glimpse of what thought might look like stripped to its essentials, a rhythm of interference and resolution, of presence and absence. As we move gently onward, the horizon begins to narrow again. We've seen how information connects, how it expands, how it computes. Now we'll ask what happens when those same quantum principles are carried to their extremes, to the smallest distances the universe allows, where space itself begins to blur. The path now carries us toward the Planck scale, the ultimate frontier of physics, where even time may begin to stutter and where the very notion of measurement begins to lose its meaning. If we follow the path a little deeper, we find ourselves standing at the edge of measurement itself, a place where even the act of asking how small begins to lose its meaning. This is the realm of the Planck scale, the smallest ruler the universe permits. Here, distances and durations shrink to limits so extreme that the smoothness of space dissolves, and the idea of before and after starts to flicker like candlelight in a strong wind. To understand where this limit comes from, imagine that every constant of nature, the speed of light, the strength of gravity, and the grain of quantum action are threads woven together into a single fabric. When physicists combine these three threads, light's speed, gravity's pull, and Planck's tiny constant, they discovered natural units that belong to the universe itself. From this weave arises a length so small, it's almost unthinkable, about 10 to the power of minus 35 meters. That's a decimal point followed by 34 zeros and a 1. A scale so tiny that if you magnified an atom to the size of the solar system, the Planck length would still be smaller than a grain of dust drifting between planets. Numbers like that strain the imagination, but perhaps we can picture it another way. Suppose you tried to measure something that small, say, to shine a beam of light to probe a region the size of the Planck length. You'd need light so energetic, so concentrated, that its own gravity would curve space around it, forming a microscopic black hole. In trying to look closer, you would erase the very thing you hope to see. The universe politely refuses to be examined beyond that limit. Below the Planck length, measurement collapses into self-contradiction. It's like trying to weigh a feather with a hammer. The act of measuring destroys what you're measuring. At scales larger than this, space behaves like a calm ocean, continuous, smooth, obedient. But at the Planck scale, the calm breaks into foam. Quantum fluctuations churn space-time itself into restless froth, a ceaseless exchange of energy and geometry. Some physicists call it quantum foam, an image that feels almost tangible, tiny bubbles of space-time appearing and vanishing in an instant, stretching and popping like breath on water. It's a poetic way of saying that even emptiness isn't empty. The vacuum hums with activity, a constant whisper of creation and annihilation. The Planck time, the smallest tick of the cosmic clock, is equally humbling. It's the time it takes light to travel one Planck length, about 10 to the power of minus 44 seconds. Nothing meaningful can happen faster, because below that interval, time itself stops making sense. The very idea of duration depends on events, and at that depth, events blur together. The universe no longer remembers which came first. It's a strange thought, that reality has a smaller scale, a base pixel beyond which it cannot be divided. For centuries, humans assumed that nature was continuous, that we could keep zooming in forever. Atoms, nuclei, quarks, strings, maybe smaller still. But the Planck scale seems to mark a boundary between what can exist and what cannot. It's not just smallness, it's finality, the smallest note in the cosmic symphony, beneath which the music dissolves into silence. You might imagine that beyond this point there lies another world, a realm of pre-geometry, where space and time themselves are emergent, not fundamental. Some theories suggest that space-time could be woven from discrete threads of information, like a vast tapestry, where each intersection is a quantum connection. Others picture it as loops, knots, or vibrating strings, their harmonies giving rise to the illusion of continuity. But all agree on one thing. At this scale, the usual rules of physics no longer apply separately. Quantum mechanics and gravity, the two great pillars of our understanding, become inseparable partners in the same unfinished equation. To get a sense of what this means, think of trying to combine two languages that were never meant to coexist, one describing the curvature of the cosmos, the other describing probabilities of particles. Each works perfectly in its own realm, relativity for the vast, quantum theory for the tiny. But at the Planck scale, they overlap, and both begin to stutter. The grammar of space and the vocabulary of chance start to blend into something new, something we don't yet fully speak. It's tempting to see this as a failure, that we simply haven't found the right theory yet. But there's also a more poetic way to look at it. Perhaps the universe is reminding us that comprehension too has a horizon. Just as you can't stand inside a painting and see the whole canvas, maybe there are aspects of creation that can't be viewed from within creation itself. The Planck scale might not be a barrier to discovery, but an invitation to humility. Still, the limit is not just philosophical, it's physical. Every object we observe, every measurement we make, carries with it a faint imprint of this smallest scale. It defines the density at which black holes form, the energy where space ripples into gravity waves, the threshold beyond which our equations dissolve. It's the quiet signature of the universe's granularity, a soft reminder that even infinity has texture. And yet, despite its elusiveness, the Planck scale may hold the key to everything. Many physicists suspect that it's here, in the mingling of gravity and quantum uncertainty, that the blueprint for the cosmos resides. The laws that govern galaxies might be the same that dance invisibly in that trembling foam. Perhaps the vastness of space is only the echo of that microscopic vibration, scaled up beyond recognition. When you look at a clear night sky, filled with the glow of 1 billion suns, it's easy to think of the universe as boundless. But each of those stars, and even the darkness between them, rests on a foundation far smaller than light itself, a flaw so fine that it defines what it means for anything to exist at all. The greatest scales rise from the smallest. The infinite is built upon the infinitesimal. From here, our quiet journey carries us toward the places where those two domains, quantum and gravity, meet in full force. The most mysterious laboratories of nature lie not in particle colliders, but in the hearts of black holes, where the Planck scale isn't theory but daily reality. There, the curvature of space reaches its limits, and the whispers of quantum foam swell into a thunder that even light cannot escape. That's where our story now turns, to the strange, peaceful darkness where gravity composes silence. If we drift further into the darkness where the smallest and the largest meet, we find a place where equations fall silent and intuition gives way to wonder. It is the realm of black holes, places where gravity becomes so powerful that even light cannot escape. They are the natural laboratories of the universe, where quantum physics and general relativity meet face to face, and where reality seems to fold in on itself. A black hole begins innocently enough. Take a massive star, many times the size of our sun, and let it burn through all its fuel. When the fire dies, nothing remains to hold up the star's weight. Gravity takes over, pulling everything inward, tighter and tighter, until the atoms themselves collapse. In the final instant, matter is squeezed beyond imagination. The entire star, millions of kilometers across, shrinks into a point so small that it defies the meaning of space. Around that point, gravity curves the surrounding region into what we call an event horizon, a one-way boundary. Once something crosses it, even light cannot turn back. From far away, this boundary looks calm and smooth, like the surface of a black sphere hanging in space. But it's not a solid wall. It's a region of no return, a threshold where time and space exchange their roles. For an outside observer, anything falling in seems to slow, red shifting into darkness, never quite crossing the edge. For the falling traveller, the passage is quick and silent, and what waits inside is hidden from the rest of the universe. This duality, one story for the distant viewer, another for the infalling one, is the first hint that black holes are not just objects, but paradoxes made real. In the 1970s, physicist Jacob Bekenstein made a surprising proposal. He realized that if a black hole hides information behind its horizon, it must have entropy, a measure of disorder or missing information. And that entropy, he found, should be proportional not to the volume inside but to the area of the horizon itself. It was as though the surface of a black hole held all the secrets of what had fallen in. The boundary, not the interior, stored the memory. In Bekenstein's words, the surface knows what the inside forgets. Then came Stephen Hawking. Building on quantum field theory, he showed that black holes are not entirely black. The vacuum around them, when seen through quantum eyes, seethes with fleeting pairs of particles that appear and vanish. Occasionally one particle escapes while its partner falls in, stealing a tiny bit of the black hole's energy. To a distant observer, the black hole glows faintly, not with light, but with what we now call Hawking radiation. The smaller the black hole, the hotter it glows. The larger it is, the colder it becomes. In this soft exchange, darkness itself learns to breathe. This discovery was revolutionary because it united the two great languages of physics, gravity and quantum theory. Hawking's calculation whispered that the event horizon behaves like a thermodynamic surface. It has temperature, entropy, and can even evaporate over unimaginable timescales. It was as though space-time itself had gained a pulse. Black holes, once thought of as endpoints, became dynamic and alive, but there was a mystery. If black holes can radiate and shrink, what happens to the information about everything that fell inside? Does it vanish forever? Quantum mechanics insist that information can never be truly lost. It can change form, scatter, hide, but not disappear. Yet relativity seemed to say the opposite. Once past the horizon, information is gone for good. The two pillars of modern physics stood facing each other like reflections in a dark mirror, each true, yet seemingly irreconcilable. This tension became known as the black hole information paradox. To some, it was a crisis. To others, a compass pointing toward a deeper truth. Over the decades, physicists tried to reconcile the two stories. Some suggested that information might be encoded in the radiation itself, that as a black hole evaporates, it releases its secrets bit by bit, like embers drifting from a dying fire. Others imagined that the horizon acts as a holographic screen, recording every detail of what enters, so that nothing is truly lost, only transformed. Whatever the answer, the implications are profound. If a black hole's entropy depends on its surface area, then perhaps this rule applies not just to black holes but to everything, every region of space, every volume of the universe. Maybe information is always stored on boundaries, not interiors. That idea, whispered by Bekenstein and confirmed by Hawking's radiation, became one of the cornerstones of what we now call the holographic principle. The notion that the universe itself might be a projection from a deeper layer of information. It's poetic to think that the darkest places in the cosmos, these silent, invisible spheres, might be the very ones that preserve memory, that hold the story of everything that has ever fallen in. Black holes, in this view, are not erasers, but archivists. Their horizons are pages written in a language of geometry and entropy, waiting to be translated. Every flicker of Hawking radiation that escapes is like a letter being slowly mailed back to the cosmos. Standing at this intersection of quantum mechanics and gravity, we begin to see how fragile our understanding of space really is. A black hole isn't merely a place, it's an event, a relationship between energy, curvature, and time. The closer we look, the less distinct these ideas become. Perhaps space itself is a fluid, shaped by the flow of information. Perhaps the geometry we call gravity is nothing more than the collective behaviour of countless entangled quantum states, the way warmth emerges from the random motion of molecules. When you gaze into an image of a black hole, that dark circle surrounded by fire captured by the Event Horizon Telescope, what you're really seeing is this union, the calm of Einstein's curvature meeting the restless whisper of quantum fields. The edges glow not because of what's inside, but because of how the outside responds to the boundary between knowing and not knowing. It's a reminder that the universe often hides its deepest truths in plain sight, wrapped in silence. As our quiet exploration continues, the path leads us from these cosmic vaults toward an even more profound idea. If information can live on surfaces, and if black holes store their secrets on their horizons, then perhaps the same principle applies to all of space-time. Maybe the universe itself is a vast hologram, a three-dimensional reality encoded on a distant two-dimensional boundary. The next step in our journey brings us to that shimmering edge of understanding, to the library at the border of existence, where the pages of reality are written not in matter or energy, but in information itself. If we follow the light that escapes a black hole, we begin to glimpse something astonishing, a pattern, faint but persistent, that suggests the entire universe might be written on its edges. The idea began as a mathematical curiosity and grew into one of the most beautiful possibilities in physics, that reality, as we know it, may be holographic. That everything we see and feel, stars, galaxies, even the air in our lungs, could be the three-dimensional shadow of information encoded on a distant surface. It's a thought both humbling and strangely comforting, that the cosmos itself might be a kind of library, each page a boundary where information and existence meet. Let's return for a moment to the black hole, that silent vault of gravity. When Bekenstein first noticed that its entropy grows with the area of its horizon, not the volume, inside he was unknowingly touching the edge of something vast. It meant that the amount of information needed to describe everything within a region of space is limited by the area of its boundary, not by how much room lies within it. In ordinary life, that's the opposite of what we expect. The number of books in a library depends on its size, not the surface of its walls. But in the language of the universe, the walls hold the words, not the shelves. The story is written on the boundary. When Stephen Hawking's calculations confirmed that black holes radiate and that their temperature is tied to this entropy, a new picture emerged. The information about everything that falls into a black hole is somehow woven into the surface itself. The horizon becomes a kind of cosmic archive, each tiny patch storing one bit of information. The smaller those patches, the more information they hold, until we reach the Planck scale, the smallest meaningful unit of area. Beyond that, the very idea of smoothness dissolves. It's as if the universe itself is pixelated, each point of space-time holding a single grain of data. From this insight came a daring generalization. Maybe black holes aren't unique. Maybe all of space follows this rule, that every volume of the universe can be described entirely by information living on its boundary. This became the heart of the holographic principle, an idea first articulated by Gerard de Hooft and later refined by Juan Maldacena in the 1990s. Maldacena's work offered a concrete example. A world with gravity in 3 dimensions could be exactly equivalent to a world without gravity living on its 2-dimensional boundary. One side described geometry and motion, the other described quantum fields and information, 2 languages telling the same story, written on different pages of the same book. It's difficult to overstate how profound this is. For centuries we've thought of the universe as something that happens within space, as though space were a container, and we were the contents. But the holographic idea suggests the opposite, that space itself is an illusion arising from the relationships between bits of information. In this view, location, distance, even time might emerge from the degree of entanglement between quantum states. Where entanglement is strong, space appears smooth and connected. Where it weakens, space stretches or tears. Geometry in this telling is not a stage. It's a song played by information. You can think of it like a woven fabric. Each thread represents a connection between quantum bits, and the strength of their weave determines the shape of the cloth. If the threads are tangled tightly, the fabric bends into curves, loosen them, and the surface flattens. In this sense, space-time isn't built from matter or energy, but from relationships, from the quiet conversations that information has with itself. The universe is less a machine and more a network, humming softly in every direction. One of the most poetic ways to imagine this is as a library. Picture yourself walking along a vast wall inscribed with tiny glowing symbols, each representing a bit of information, each encoding a fragment of reality. Somewhere on that wall lies the complete history of a single star, a planet, a living being. Deeper still, perhaps, are the instructions for the laws of nature themselves, the grammar that governs the sentences of existence. And what you experience as 3-dimensional reality is the holographic projection of those symbols unfolding like a story read from the surface of the cosmos. This vision doesn't diminish the physical world, it deepens it. The warmth of sunlight on your skin, the pull of gravity under your feet, the slow drift of clouds, all are still real. But beneath them lies a subtler reality, patterns of information constantly rearranging, copying, entangling, erasing. Every interaction, every exchange of energy, changes the writing on that cosmic wall. The universe is both author and reader, continuously editing its own story. Even the great paradox of black holes, whether information is lost when they evaporate, begins to soften under this light. Modern research suggests that as a black hole radiates, its emitted particles gradually encode the information that was once hidden behind the horizon. Over time, the radiation carries the story back into the universe, preserving the law of conservation of information. It's as though the black hole whispers its memories into the void, syllable by syllable, until only silence remains. This image of a universe where every boundary is a record and every interaction an exchange of meaning blurs the line between physics and philosophy. It suggests that reality is not a solid thing, but an ongoing conversation. When we observe, we participate in that dialogue. Our measurements, our thoughts, our questions, they all leave faint marks on the surface of the cosmic library. Perhaps that's what consciousness truly is, the universe turning one of its pages and briefly recognizing the words written there. The holographic principle also gives new weight to an old truth, that simplicity and depth are not opposites. A single surface can contain infinite complexity, just as a simple melody can carry endless emotion. In a way, the entire cosmos could be described by a single equation or a single principle, if only we knew how to read it. But maybe it's better that we don't. A mystery too easily solved becomes smaller. A mystery that unfolds slowly keeps us awake, keeps us listening. If you imagine the night sky again, its quiet scattering of light across the dark, think of it not as a vast emptiness, but as the curved page of that cosmic library. Every star, every photon, is a word written long ago, still glowing faintly. The boundaries of the universe are not walls keeping us in, they are pages inviting us to read, and as we turn those pages, we begin to see that the story of space is also the story of information, and that every thread of entanglement is part of the grand weave of meaning. From here, our gentle path begins to rise once more, from the smallest to the grandest scales. If the universe is woven from information, then the same quantum threads that shape black holes and galaxies must also have given rise to the stars themselves, and to us. Our next step carries us from the edges of space-time into the luminous birthplaces of the cosmos, where quantum seeds once grew into galaxies and the infinite took shape in the glow of creation. If we follow the trail of quantum law beyond the edges of black holes and back into the luminous sky, we find another kind of balance. Not a paradox of darkness, but of survival. For even stars, those great furnaces of light, owe their endurance to the quiet rules of the quantum world. Somewhere inside the hearts of dying suns, a delicate negotiation unfolds between gravity, which forever pulls inward, and a mysterious quantum pressure that pushes back. Without this invisible resistance, every star would end in collapse, and the night would be filled not with pinpoints of light, but with endless silence. The story begins at the end of a star's life. When a star like our Sun exhausts its fuel, it can no longer fuse hydrogen into helium, the process that has, for billions of years, supported it against its own weight. The outward pressure fades, and gravity begins to tighten its grip. The star contracts, its outer layers drift away, and what remains is a dense core, a white dwarf, no larger than Earth, but containing as much mass as the Sun. In this tiny remnant, gravity is immense, squeezing the matter so tightly that atoms are forced shoulder to shoulder. You might imagine that they would simply merge into one another, collapsing into a single featureless lump. But something subtle intervenes, a rule written deep within quantum mechanics. That rule is called the Pauli exclusion principle, and it states, quite simply, that no two electrons can occupy the same state at the same time. It's a law of individuality for particles, a gentle insistence that each must have its own space in the universe. When gravity tries to pack them closer together, the electrons resist, not because they're pushing with any mechanical force, but because quantum law forbids them from sharing identical conditions. Their very identity generates pressure, an invisible cushion that halts collapse. This is called electron degeneracy pressure, though that phrase sounds far colder than the phenomenon deserves. It's really a kind of quantum stubbornness, a refusal of matter to lose its structure. The effect is astonishing. In a white dwarf, gravity pulls inward with unimaginable strength, but this quantum pressure counters it perfectly. The result is equilibrium, a star that no longer burns but doesn't fall. It simply glows, cooling slowly over trillions of years, like a cosmic ember that refuses to fade entirely. In this balance between compression and resistance, we see the universe's gentlest compromise, the Planck constant itself, that tiny measure of quantum granularity, rising to hold up the weight of a sun. But this harmony has a limit. Subramanian Chandrasekhar, a young Indian physicist in the 1930s, carried the idea to its mathematical conclusion. He asked, how much mass can a white dwarf bear before even quantum law gives way? His calculations revealed a threshold, about 1.5 times the mass of the Sun. Beyond that, not even the electron's refusal can hold gravity back. The star must collapse further, crushing atoms until electrons and protons merge into neutrons. What remains is even smaller and denser, a neutron star, where a teaspoon of material weighs billions of tons, and if the mass is greater still, the collapse continues until the star disappears entirely into a black hole, where the concept of matter loses meaning. You could think of Chandrasekhar's limit as a conversation between constants: the speed of light, the strength of gravity, the quantum rule of exclusion, all whispering together to decide the fate of stars. It's not an argument, but an agreement. The universe, in its quiet logic, allows balance only up to a point. Beyond that, it yields to transformation. Even equilibrium, it seems, must one day bow to change. It's humbling to realize that this balance governs not only stars, but also us. The very atoms in your body exist because of that same quantum principle. Without it, electrons would spiral into nuclei, and matter would collapse into featureless uniformity. Everything solid, everything distinct, everything alive depends on the tiny insistence of particles to remain unique. The rule that keeps a white dwarf from collapsing is the same one that keeps your body from vanishing into itself. It is the universe's quiet respect for individuality, a kind of cosmic courtesy encoded in the smallest scales of existence. In the grand view, this quantum pressure is like a heartbeat within the cosmos. It pulses in every atom, holds up the relics of dying suns, and defines the threshold between endurance and surrender. White dwarfs are scattered across the galaxy like pearls of frozen light, each one a monument to the resilience of quantum law. When you look up at the night sky, you may be seeing not just the brilliance of living stars, but the faint glimmers of these ancient survivors, suns that have burned their last and now rest in quiet equilibrium, upheld by principles written at the birth of reality. There's something deeply poetic about this. The same constant that determined the colour of Planck's glowing metal in 1900, the same grain of energy that Einstein followed to discover the photon, also governs the afterlives of stars. What began as a microscopic principle has become the scaffolding of galaxies. From the whisper of an electron's resistance comes the endurance of entire worlds. It is a reminder that in the universe, smallness and vastness are never truly separate. They are notes in the same melody. If you close your eyes for a moment and imagine one of these white dwarfs, suspended in the darkness, its light fading slowly through ages longer than all of human history, you might sense the peace of it, a balance so precise that it can last beyond comprehension. Each photon that escapes its surface is a farewell, but also a testament. Gravity has not won, neither has collapse. The star remains, quiet but unbroken, a memory of what it once was and a promise of what the universe allows things to become when all motion ceases. As we drift further into this cosmic story, our attention turns from the embers of stars to the seeds of galaxies themselves, to the early universe where quantum tremors, tiny beyond imagining, swelled and stretched until they became the architecture of everything. The same rules that hold up stars also gave shape to the heavens. What began as microscopic noise would one day become the grand design of the cosmos. If we follow the faint trail of light backward, past the white dwarfs and the dying suns, past the birth of stars themselves, we reach a time when there were no stars at all, only a hot, dense ocean of energy, expanding and cooling. In that primordial sea, everything that would one day become galaxies, planets, and people was still only potential. And yet, within that glowing fog, something delicate stirred. Tiny fluctuations, quantum in origin, rippling through the newborn universe. They were unimaginably small, mere whispers of unevenness, but they would become the seeds of every structure we now see in the sky. The grandest galaxies owe their existence to these quantum tremors, amplified by time and gravity into the architecture of the cosmos. To picture this, imagine an endless ocean of mist lit from within. At first, it is perfectly uniform, no waves, no currents, just light and heat. But at the smallest scales, even this perfection cannot hold. Quantum mechanics insists on uncertainty. Even emptiness cannot remain still. So, the early universe trembled with fluctuations, tiny variations in density, as if space itself were breathing. Some regions were slightly denser, others slightly thinner, each deviation no greater than 1 part in 100,000. In ordinary language, it means that for every 100,000 atoms there was 1 extra in some places, 1 fewer in others, a small difference, but enough to tilt the future. Then came inflation, a brief, extraordinary burst when the universe expanded faster than any physical thing ever could, stretching those tiny fluctuations to cosmic scales. It happened within the smallest fraction of a second, a breath shorter than any clock could measure. The ripples that had once lived on subatomic scales were blown up to sizes millions of light years across, freezing them into the fabric of space itself. The pattern of that early trembling became the blueprint for everything that followed, where galaxies would form, where voids would open, where gravity would gather matter into stars. You could say that the first structure of the cosmos was drawn by quantum randomness, magnified by cosmic breath. Billions of years later, when we look up at the sky with our instruments, we can still see the faint echo of those first ripples. It arrives as a soft, uniform glow called the cosmic microwave background, the afterglow of creation. It's not visible to the naked eye, but it fills every corner of space, a kind of fossil light. Within that glow, there are gentle variations in temperature, small patches slightly warmer or cooler than their neighbours, just as the early density differences once were. When we map them, we see a pattern like frost spreading across a window pane, subtle, intricate, yet full of order. Those shimmering spots are the fingerprints of the universe's earliest moment of creativity. Every star, every cluster, every galaxy you can imagine grew from those faint traces, the way coral grows around the smallest specks of sand. It's astonishing to think that the cosmos we inhabit, its vast filaments of galaxies, its empty voids, its swirling clusters, all emerged from fluctuations smaller than atoms. The entire visible universe is in a sense the magnified image of quantum uncertainty. The randomness that once seemed like noise became the foundation of structure. Without it, the universe would have been too smooth for gravity to sculpt anything. There would have been no stars, no light, no chemistry, no life. Imperfection, it turns out, was the condition for beauty. When the Planck satellite mapped this cosmic background with extraordinary precision, it confirmed what theory had long predicted, that these early fluctuations followed a specific pattern, neither too strong nor too weak, a perfect balance that allowed matter to clump without collapsing. It was as if the universe had tuned its first chord with impossible precision. Any other note, any other scale of fluctuation, and the song of creation would have ended before it began. But there's a deeper poetry here. The same principle that allows electrons to exist in superposition, the same quantum fluctuations that flicker in every vacuum, were responsible for painting the first texture of reality. The micro became the macro. The smallest ripples in the fabric of space-time blossomed into galaxies. You and I, made of atoms forged in stars, are, in a very literal sense, children of those first tremors. The randomness that danced at the edge of nothingness gave birth to the order of everything. It's easy to imagine the early universe as violent or chaotic, but there's a quiet rhythm beneath that image. Each fluctuation was like a note in a song that would take billions of years to reach its crescendo. Gravity gathered the denser regions, pulling gas into clouds that glowed and ignited. Stars were born, died, and spread their ashes across space. Galaxies merged and swirled, and through it all, the original quantum blueprint continued to echo, a pattern of light and darkness that still guides the cosmic web we see through telescopes today. Perhaps the most moving realization is how close it all came to not happening. Had those initial variations been just a little smaller, the universe would have remained smooth, a dark, cold fog with no stars. If they had been larger, gravity would have crushed everything into black holes before galaxies could form. Our existence rests on the balance between these two extremes, on fluctuations just strong enough to build, but gentle enough to endure. It's a balance so fine that one could almost hear the universe holding its breath. When you step outside on a clear night and see the faint band of the Milky Way, you're looking at an echo of those ancient ripples. Every glimmer, every cluster of light is part of that frozen music. The photons reaching your eyes tonight began their journey over 13 billion years ago, tracing paths shaped by the same quantum whispers that stirred the first dust. To look up is to read the oldest record, a story written in light, still legible across eternity. From here, our quiet journey rises further still, carrying us across the ladder of scales, from those smallest seeds of creation to the vast structures that now fill the cosmos. If we keep climbing step by step from atoms to galaxies to the observable edge of the universe, we might find something surprising, that we ourselves live right in the middle, between the smallest possibilities and the widest horizons. And that realization, that the human scale is not small but central in its own way, will be the next gentle turn of our story. If we keep climbing upward from those first quantum ripples, we begin to see the universe as a ladder, each rung a different scale of existence, each step revealing a new kind of beauty. The smallest and the largest are not opposites, they are reflections. Somewhere between them lies us, the observers, balanced between atoms and galaxies, between fleeting moments and the lifetime of stars. To walk this ladder in our mind is to glimpse how vast the universe truly is, and how gently connected every level of it remains. Let's begin at the bottom, at the smallest rung that nature allows. At the Planck length, about 10 to the power of minus 35 meters, space ceases to be smooth. It becomes grainy, restless, like the foam at the edge of an invisible sea. Time too loses its steady rhythm. You could say this is the level where the equations of physics begin to whisper rather than speak. Here, the world flickers between being and not being, and the only certainty is uncertainty itself. Beyond this, nothing can be measured without destroying the very thing one tries to see. Climb one step higher, and we enter the realm of subatomic particles, quarks, electrons, neutrinos. These are not tiny marbles, but patterns of probability, small vibrations in the quantum field that fills all space. Each particle is both local and everywhere at once, a ripple that can spread or collide, but never quite stand still. The proton, a cluster of quarks bound together, is roughly 100 trillion times larger than the Planck scale, an unimaginable gap, yet still far smaller than anything our eyes can see. Step higher still, and atoms appear. Each one is a miniature solar system, though emptier than we might think, a tiny dense nucleus surrounded by a vast halo of probability where electrons dance. If the nucleus were the size of a grain of rice, the atom itself would stretch for several football fields, and yet those clouds of uncertainty overlap and bond, forming the familiar textures of matter, air, water, stone, and skin. It is at this scale that the rules of chemistry and life begin to unfold, rules born from quantum probabilities that have found a way to stabilize. From atoms, we move to molecules and cells, the scale of biology. Within each living cell, molecular machines fold and unfold, reading the code of life, transforming chemistry into awareness. The distances here are measured in nanometers, billionths of a meter, still far above the quantum world, but small enough that its influences never truly fade. Life, in its essence, is quantum behavior magnified to stability. The spark of consciousness that allows us to wonder about these scales is built from matter that, at its root, obeys uncertainty. Continue the climb, and we reach the human scale. Meters, seconds, heartbeats. Here, reality feels familiar, dependable, and still. Gravity is gentle, light travels fast enough to seem instant, and we measure time by the turning of our planet rather than the trembling of particles. We live in a zone where the universe's extremes balance out, small enough to touch the quantum through our atoms, large enough to feel the pull of galaxies through our tides. If the cosmos is a song, we are tuned to its middle octaves. Now, let's take larger steps. Mountains rise from valleys, continents drift across oceans. The Earth itself, with its thin shell of atmosphere, is just one world among billions circling billions of stars. At this planetary scale, the quantum laws that govern atoms merge seamlessly into the classical patterns of orbits and tides. A cloud forming in the sky, a wave breaking on the shore. Each is the macroscopic echo of microscopic rules. The same physics that shapes the spin of an electron also determines the curve of the Earth's horizon. The connection is unbroken, it's simply stretched. Further up the ladder, we reach the realm of the stars themselves. They burn through nuclear alchemy, turning hydrogen into helium, releasing the light that paints the night. Around them, planets orbit like quiet companions. On scales of millions of kilometers, gravity is the composer, writing its symphonies in the arcs of orbits and the dance of light. But even here, quantum mechanics still plays the flute in the background, in the fusion reactions that keep the stars alive, in the behavior of photons that escape from their cores. The vast and the tiny sing together, climb higher, and galaxies bloom like islands of light, each containing hundreds of billions of stars. The Milky Way itself stretches more than 100,000 light-years across, its spiral arms turning slowly through time. To cross it at the speed of light would take longer than the span of all recorded human history, multiplied by 10,000. And yet, even at this grand scale, the arrangement of galaxies follows patterns seeded by quantum fluctuations in the early universe, the same faint ripples we met in the previous session, now written across cosmic distances. Step beyond that, and we see clusters of galaxies bound together by gravity, threads of matter and dark energy weaving the structure of the universe. The observable cosmos extends roughly 46 billion light-years in every direction. Beyond that, we don't yet know. Perhaps more universe, perhaps something stranger. But within this vastness lies a profound symmetry. The ratio between the Planck length and the size of a human being is roughly the same as the ratio between a human and the observable universe. We live quite literally in the middle, not in power or importance, but in scale, poised halfway between the smallest tremor of space and the broadest expanse of stars. That balance is more than coincidence. It's a perspective that grants us the ability to see both directions. We can peer inward with microscopes and outward with telescopes, tracing the universe from quarks to quasars. We can hold in our minds both the fragility of the quantum world and the grandeur of the cosmic. The middle, it turns out, is not a place of smallness, but of connection. It's where meaning emerges, where the infinite above and the infinitesimal below meet in the act of awareness. If you imagine standing at night beneath the open sky, you are part of this ladder of scales. The atoms in your breath were once forged in stars. The photons entering your eyes began their journey across light years. The warmth you feel on your skin comes from quantum energy released long before your birth. You're both observer and participant, suspended between the micro and the macro, between what is fleeting and what seems eternal. As we continue our quiet ascent, the next step leads from the physical to the reflective, from the structure of the universe to the mystery of knowing it. the question begins to change, not just what the universe is, but what it means for it to be observed at all. If we are made of the same matter as the cosmos, what does it mean that we can look back and wonder? Perhaps awareness itself is the universe's way of seeing its own reflection, and that is where our journey now turns, toward the strange, luminous idea of a universe that thinks about itself. If we follow the ladder of scales to its quietest rung, not up or down but inward, we reach a point where the act of seeing becomes part of the story itself. The universe has been unfolding for billions of years, forming stars, galaxies, and planets. But only recently did it acquire a peculiar ability, the power to reflect on its own existence. Through the lens of human consciousness, and perhaps others scattered somewhere across the cosmos, the universe looks back at itself. It becomes both the observer and the observed, both the dream and the dreamer. This idea may sound poetic, but it arises naturally from the strange logic of quantum mechanics. In that world, observation is not a passive act. It's not like watching a play unfold from a seat in the audience. To observe is to participate, to choose, among many possibilities, the one that becomes real. When a photon meets a detector, or an electron strikes a screen, the field of potential collapses into a single event. Reality, it seems, solidifies when it is noticed. It's not that our minds create the universe, but that the universe and our awareness of it are two sides of one unfolding process. You could imagine it this way. In the early cosmos, matter and energy were a vast ocean of uncertainty, waves of probability existing in all possible forms. Over time, through interaction, through measurement, through the constant exchange of information, that uncertainty condensed into structure, into atoms, stars, and life. In a sense, every act of measurement, from the quantum level upward, is the universe making choices about itself. When we observe, we simply continue that ancient pattern. Consciousness becomes the latest chapter in a story that began long before thought, the story of reality coming to know itself. Different thinkers have tried to explain this relationship in many ways. Some say that measurement forces the universe to choose, that before we look, all possibilities coexist, and only observation crystallizes one into being. Others believe all possibilities already exist side by side, like pages in a cosmic book, and that our perception simply turns from one page to another. Some prefer to think of it as decoherence, that the world naturally divides into branches of outcomes, each consistent within itself. These are not competing doctrines, but lullabies for the same mystery. Each tries to describe how the act of seeing and the fabric of being are inseparable. What all these ideas share is a quiet acknowledgement that awareness is not an accident. It is woven into the process of reality. The equations of physics do not single out human consciousness. They apply to every act of information exchange, every interaction where something becomes defined. But at a certain level of complexity, this process folds back upon itself. The universe produces beings capable not only of participating in reality, but of recognizing that participation. When you gaze at the night sky, you're not looking at the universe. You're the universe looking at itself. Your eyes, your thoughts, your heartbeat, all are expressions of that same cosmic field, momentarily arranged into curiosity. There is something deeply comforting in this view. It means that consciousness is not an anomaly flickering briefly in an indifferent void. It is a continuation of the same natural laws that shape galaxies and stars. The atoms in your brain are governed by the same quantum rules that once sculpted the early cosmos. The thoughts that move through your mind are patterns of energy, no different in essence from the ripples that move through space-time. In that sense, awareness is not outside of nature, it is nature becoming aware. You could think of existence as a great mirror, one side reflecting matter, the other reflecting meaning. For most of cosmic history, the mirror was dark, unlit by self-recognition. Then, in the last fraction of cosmic time, Somewhere on a small blue world, the mirror caught the faint glow of understanding. Life evolved, learned, built tools, and eventually turned its gaze outward. The same laws that governed hydrogen and helium had quietly assembled eyes capable of seeing, minds capable of wondering, and hearts capable of awe. That moment, when awareness bloomed, was not separate from the Big Bang. It was its continuation. This realization has a subtle effect on how we think about our place in the cosmos. It replaces isolation with intimacy. We often describe ourselves as tiny in comparison to the universe, mere specks of dust adrift in endless space. But from another angle, the universe is incomplete without the perspective we bring. Without consciousness, all of existence would remain an unfinished symphony, notes without ears to hear them. In us, and perhaps in countless others we have yet to meet, the cosmos achieves something profound. It listens to itself. There's a quiet humility in knowing that our thoughts are temporary, yet universal in origin. The neurons that fire when you feel wonder were once stardust. The photons that strike your retina were born in the cores of stars billions of years ago. Each thought, each memory, is the afterglow of creation reshaping itself into awareness. You are, in every measurable sense, a continuation of the Big Bang, an expanding wave of consciousness tracing the echoes of its own beginning. Philosophers sometimes ask, if the universe can think about itself, does it also dream, remember, or hope? Science cannot answer that, but it can remind us that reflection is a natural product of complexity. The same laws that let atoms bind and stars ignite also allow minds to arise, not through magic, but through the slow accumulation of structure and sensitivity. The awareness that asks why is the same pattern that allows particles to interact. The difference is scale, not essence. So, when we speak of the universe that thinks about itself, we are not proposing a mystical idea, but observing a natural progression, from the quantum to the conscious, from probability to poetry. Awareness is the universe made intimate. It is the cosmos in conversation with itself, through us. That's why, in every quiet act of curiosity, when you wonder about the stars or trace the shape of an idea, you're not separate from the vastness you study. You're part of its unfolding, one of its thoughts in motion. As our journey continues, we will begin to look ahead, to how this awareness might shape the future. The same principles that govern entanglement and information are now guiding our technology, linking minds and machines, and preparing humanity for a new kind of exploration, one that stretches not only across space, but across understanding itself. From the flicker of quantum awareness, we now turn toward the dawn of quantum civilizations, a time when the universe's consciousness begins to reach beyond the stars. If we follow the thread from thought to technology, we arrive gently in the present, an age where the strange principles that once belonged only to the world of theory are now becoming instruments we can touch. For over a century, quantum physics has described how the universe behaves in silence at scales smaller than imagination. Yet only recently have we begun to learn how to listen to that silence carefully enough to use it. We stand at the threshold of an era when our machines are beginning to hum in harmony with the laws that govern the stars themselves. This is the dawn of the age of quantum tools. To understand what makes this era different, imagine standing before one of the new quantum computers, a tall, gleaming cylinder suspended in a halo of cables and tubes. Around it, the air is chilled to near absolute zero, a temperature so low that atoms barely move. The reason for such stillness is simple. Quantum states are fragile, easily disturbed by heat, vibration, or even the faint touch of light. To hear their whisper, we must first quiet the world around them. Inside that cold chamber, qubits, those tiny compasses of probability, perform their delicate dance, existing in many states at once, then merging back into one outcome. It's a machine that doesn't calculate the way a classical computer does. It listens to possibility and lets interference find the answer. There's something almost monastic about such a device. It must be kept in a perfect balance between isolation and connection. Isolated enough to preserve coherence, connected enough to be controlled and read. Scientists sometimes describe the problem of decoherence as a kind of forgetfulness, a tendency of qubits to lose their memory of being multiple things at once. Every interaction with the environment, a vibration, a stray particle, reminds them of the larger world, forcing them to choose one outcome prematurely. Much of modern quantum engineering is an art of patience, learning how to build an environment that allows uncertainty to linger just long enough to be useful. It's as if humanity is learning to extend the moment before a coin lands, to keep the possibilities alive until they can be read as information. The progress has been slow but profound. In laboratories around the world, researchers trap ions in magnetic fields, guide photons through lattices of mirrors, and build circuits from superconductors so pure they carry current with no resistance. Each qubit is a whisper of probability suspended in time. And when many qubits are entangled, their combined state becomes richer than any machine of the past could ever handle. In principle, these networks can perform computations that would take classical supercomputers longer than the lifetime of the universe. The challenge is not to dream of infinite speed, but to sustain fragile harmony. Quantum computing is less a race for power than a study in precision, an exercise in learning how gently reality must be touched to reveal its depth. Yet not all quantum tools are built for calculation. Some are designed for measurements so subtle that they redefine what we mean by time itself. Take the new generation of atomic and optical clocks. They tick not by gears or pendulums, but by the oscillations of light interacting with atoms, vibrations so regular that they lose only a second every few billion years. These clocks can sense gravity, motion, and even the slow curvature of Earth's shape as tectonic plates move. Time, once an abstraction, has become a field we can map with exquisite detail. Each tick is a conversation between light and matter, a shared rhythm between human invention and cosmic law. Elsewhere, scientists use entangled particles to push the limits of communication. In 2017, a satellite named Micius, orbiting high above Earth, successfully transmitted entangled photons to 2 ground stations separated by more than 1,000 kilometers. Each photon pair shared the same invisible connection, their polarizations perfectly correlated despite the vast distance between them. It was the first large-scale demonstration of quantum key distribution, a form of encryption so secure that any attempt to eavesdrop would instantly reveal itself. It proved that entanglement, that delicate bond Einstein once called spooky, could reach into orbit and still hold true. 2 photons, 1 story, stretched across 1,000 kilometers of air and cloud and silence. What's remarkable about these achievements is not just their technical precision, but their philosophical resonance. For centuries, humans have built tools that separate us from nature, machines that impose order, extract power, or bend materials to our will. Quantum tools do something subtler. They ask us to listen, to cooperate with the universe's own uncertainty. They turn probability into partnership. In this sense, technology is becoming contemplative, not an act of domination, but of participation. The uses extend far beyond laboratories. Quantum sensors can measure magnetic fields so faint they can map the beating of a human heart without touching the skin. Quantum gyroscopes promise navigation without reliance on satellites, reading the rotation of the Earth itself. Quantum materials hint at computers that could operate without heat, saving energy on planetary scales. Each breakthrough, in its own quiet way, teaches us how to think like nature, to build systems that are not rigid but adaptive, not absolute but aware. If you listen carefully, you can sense the larger pattern emerging. The same curiosity that once led Planck to quantize light and Einstein to reveal its particles has now looped back to us in the form of instruments that use those same principles to explore, compute, and connect. We are beginning to hold conversations with the laws of physics at their most fundamental level. Every qubit, every photon in an entanglement experiment is a tiny handshake between human intention and cosmic possibility. It's easy to imagine how this story continues. Quantum technologies are already reaching orbit, linking distant stations and whispering across space with entangled light. Soon they may guide spacecraft, synchronize interplanetary clocks, and allow communication between worlds. The age of quantum tools is only beginning, but its tone is already clear, not loud or triumphant, but calm, precise, and almost reverent. It invites us to see technology not as a conquest of nature, but as a deepening of our conversation with it. And as this conversation grows, it will carry us outward, to the stars and beyond. Our quiet exploration now turns toward that next horizon, where these new tools will help humanity navigate among the stars, measuring not just distance and time, but our own place in the cosmic rhythm. If we drift onward from the laboratories of Earth and gaze toward the vast, quiet ocean of space, we find ourselves standing on the edge of the next great transformation, one where the quantum tools we've learned to build no longer stay anchored to the ground, but begin to guide us between the stars. For centuries, exploration has meant the same thing: sails catching wind, engines burning fuel, compasses pointing north. But the future of exploration may look less like propulsion and more like precision. In the age of quantum navigation, we may learn to move through the cosmos not by force, but by understanding, by reading the faint whispers of space-time itself. Navigation, at its heart, is the art of knowing where you are and when you are there. For sailors once guided by constellations, the stars served as timeless markers. But as we venture farther, beyond Earth, beyond the reach of radio signals or GPS satellites, the sky itself becomes too wide to navigate by sight. The distances are immense, the timing crucial, and even light takes minutes or hours to carry messages between travelers and home. What we need are clocks and sensors so accurate that they can tell us our position from the shifting breadth of the universe. That is where quantum technology enters, not as a replacement for rockets, but as their quiet companion. A quantum clock, built upon the oscillations of atoms or photons, measures time so precisely that if it had started ticking at the birth of the universe, it would now be off by less than a heartbeat. Such perfection turns time itself into a coordinate. With 2 or 3 of these clocks synchronized across space, a ship could know its position without relying on Earth at all. It could navigate by comparing its own heartbeat to the cosmic rhythm. Imagine a future spacecraft drifting between the planets. It doesn't rely on signals sent from home, but listens instead to the faint murmur of space-time, the curvature of gravity, the subtle tug of nearby worlds. On board, quantum interferometers measure how light waves overlap and shift as the ship moves. A tiny difference between 2 beams can reveal how much space is stretched or compressed. It's like hearing the quiet creak of a wooden floor and knowing exactly which board you stand on. Navigation becomes a dialogue between ship and universe, each movement answered by a measurable reply. These ideas are already more than dreams. Engineers have built prototype sensors that can detect acceleration and rotation with almost unimaginable sensitivity. Some can read the gravitational signature of a nearby mountain or the motion of underground water from meters away. Scaled up, they could sense the presence of planets, asteroids, or even the subtle ripples of gravitational waves. A fleet of such instruments could one day chart the galaxy the way ancient mariners once mapped the seas, not by guesswork, but by listening to the invisible contours of reality. In this vision of exploration, precision replaces power as the defining virtue. Instead of burning fuel to correct our errors, we'll know where we are so well that we'll waste nothing. Instead of brute force, we'll travel with grace. Light sails, thin sheets of reflective material, may ride beams of photons like modern-day galleons catching sunlight instead of wind. The idea is simple but profound: to use radiation pressure, the soft push of light itself, to propel a craft forward. The energy comes not from engines but from the stars, or from focused laser beams projected from distant worlds. Each photon, though weightless, carries momentum, and when trillions of them strike a sail, they can slowly but steadily push it across the void. Philip Lubin and other visionaries have begun to sketch the path of such missions. A probe weighing only a few grams, carried by a sail no thicker than a whisper, could reach a fraction of the speed of light. At that pace, it might cross the distance to another star within a human lifetime. There would be no crew, no fuel tanks, only the relentless push of light and the patience of centuries of curiosity condensed into a single journey. It's almost poetic. The same photons that reveal the universe through our telescopes could one day be the wind that carries us across it. And yet the real magic lies in how we would find our way once we're adrift. Beyond the familiar reach of the sun, there are no landmarks, no GPS signals, no comforting blue dot to orient us. We would rely on pulsars, rapidly spinning neutron stars that swoop the cosmos with beams of radiation as regular as the ticking of a celestial clock. By comparing signals from 3 or more pulsars, a ship could triangulate its position anywhere in the galaxy. Combine that with quantum clocks and interferometers, and navigation becomes almost sacred, a conversation between human craft and cosmic heartbeat. The deeper implication of all this is quiet but profound. Every improvement in precision expands our reach. The more accurately we measure, the farther we can go. In a way, progress in exploration is simply an evolution in attention, a refinement of awareness. The same spirit that once led sailors to follow the stars now leads physicists to follow the quiver of atomic transitions, the faint shimmer of entangled photons. Each generation navigates by finer light. If you close your eyes, you can almost hear the sound of it. Not the roar of rockets, but the soft hum of measurement, the rhythmic ticking of perfect clocks, the shimmer of laser beams spanning the void. Future explorers might travel not as conquerors, but as listeners, gliding along threads of data woven through the cosmos. Their vessels will be quiet, their paths efficient, their guidance drawn not from instinct or inertia, but from the subtle fabric of physics itself. When we finally learn to move this way, with understanding instead of urgency, space will cease to feel distant. It will become familiar, navigable, intimate. We'll no longer look up and see isolation. We'll see connection, a web of light, each node a point of awareness. Perhaps that is how exploration was always meant to be, not an escape from Earth, but a widening of perception. From here, the path opens naturally into the human side of progress. As we spread outward, we'll have to decide not only how far we can go, but how gently we should tread. The universe invites us to explore, but not to scatter or scar. The next part of our journey turns toward that quieter question: how to move through the cosmos without losing our balance, and how to build civilizations among the stars that reflect not ambition alone, but wisdom. If we follow the light of our ambitions outward, we eventually meet a question that glows even brighter than the stars themselves. Not can we go farther, but how should we go? As our reach expands beyond Earth, the meaning of exploration begins to change. It becomes less about escaping the limits of our world, and more about learning how to live within new ones responsibly. The story of civilization, after all, has never been just about movement. It's about the traces we leave behind, the footprints on each new shore, the echo of our choices in the silence that follows. When the first sailors crossed oceans, they carried their hopes, their fears, and their errors with them. Every discovery was also an impact. In space, we carry the same paradox. the drive to explore, and the duty to preserve. Our technology may have evolved, but our moral compass must still be calibrated. It must point not only toward curiosity, but toward care. Imagine for a moment Earth seen from orbit, a delicate sphere wrapped in blue and white, the only known home of life. The atmosphere looks paper-thin, almost translucent, fragile enough to vanish in a single careless act. From that perspective, the idea of conquest feels absurd. There is nothing to conquer in space, there is only to coexist. Every asteroid, every moon, every barren planet is part of a vast cosmic balance. Silent, but not meaningless. To touch them, to mine them, to colonize them, is to enter into that balance. It demands humility. Already our presence beyond Earth has begun to leave traces. Thousands of satellites circle the planet, forming constellations of metal and glass. They bring communication, observation, and knowledge, but also clutter the heavens with debris, fragments moving faster than bullets, each one capable of damaging what it once supported. Even this thin veil of orbit has become a reflection of our habits, our brilliance and our carelessness entwined. The challenge ahead is not to stop expanding, but to learn how to move through space without scattering dust, without turning the stars into another mirror of our untidiness. Some thinkers speak of orbital commons, the idea that the space around Earth should be treated like an ecological habitat, not in the biological sense, but as a shared environment. It's a place where harmony must replace ownership, where stewardship must guide invention. To navigate responsibly means to coordinate, to plan, to think in centuries rather than quarters or launches. It's a slow ethic in a fast age, but perhaps that's exactly what space requires of us. Patience, and the awareness that every trajectory continues forever. Beyond orbit, the questions grow larger. What happens when we begin mining asteroids for resources, or building habitats on the Moon, on Mars, or in free space? Who decides the boundaries of ownership? Who speaks for the places we have yet to touch? The treaties of today were written in a time when space was empty and unreachable. But as it becomes livable, those words will need to evolve. It's not only a matter of law, but of philosophy. How do we ensure that our expansion reflects the lessons we've already learned on Earth? That growth without regard becomes destruction? The answers may not come from policy alone, but from perspective. Space, by its very nature, teaches interdependence. There are no borders visible from orbit, no national colours dividing continents. From up there, humanity looks like a single experiment in survival, one fragile system suspended in darkness. To carry that awareness outward is to honour what we've learned. Colonising space will not mean repeating the history of competition. It will mean rewriting it into collaboration. Perhaps one of the most hopeful aspects of the quantum age is that it naturally encourages interconnected thinking. Entanglement, coherence, information. These are not metaphors for unity. They are the physics of it. Every quantum system reminds us that no particle exists alone. The cosmos itself is a web of relationship. If our technologies now echo that truth, maybe our societies can as well. The very principles that allow us to compute, communicate, and navigate can also guide us toward a more ethical form of expansion, one that values connection over consumption. We may even find that restraint becomes a new kind of progress. To build sustainably is not to build less, but to build wisely, to design stations and habitats that recycle, orbiters that leave no trace, missions that listen as much as they act. It's easy to imagine grand future cities on Mars or floating colonies around Saturn, but perhaps the real success will be quieter, a culture that sees exploration as participation, not extraction. To live among the stars should not mean scattering across them recklessly, but moving gently within their rhythm. You can picture it like walking into an ancient forest. Every tree is older than memory, every step disturbs something. To move through such a place without harm, you must tread softly, aware of both presence and privilege. Space will be the same, ancient, silent, immense. Every asteroid we mine, every moon we touch, will carry the weight of that awareness. We will not be visitors. We will be participants in a story much older than our species. And yet, despite these challenges, the dream remains luminous. Space offers us not only resources and expansion, but perspective. It shows us our unity, our fragility, our potential. If we can learn to act as caretakers rather than conquerors, exploration might become something purer, not an escape from Earth, but a way of cherishing it more deeply. To see the planet from a distance floating in the dark is to realize that home is not a boundary, but a relationship. The next chapters of humanity's story may well be written in orbit, in lunar dust, or under the orange skies of Mars. But their moral tone will be set here, in how we think about what it means to reach beyond ourselves. The universe is vast enough to hold every dream we've ever had, but it asks for one thing in return: responsibility. From here, our journey moves quietly forward into the farthest horizon of time. Beyond ethics and exploration lies a different kind of question, not about where we go, but how long we might endure. The cosmos stretches ahead into ages we can scarcely imagine, filled with fading stars and deepening silence. And yet, even in that darkness, there may be hope, not in survival alone, but in the persistence of thought. The next step of our story leads us into that distant future, to the long night of the universe, and to the faint but enduring light of memory. If we follow the thread of time far beyond the horizon of our lives, beyond the lives of stars themselves, we arrive in an age the universe has not yet lived, an era of cooling embers and dimming light. The cosmos, vast and brilliant as it seems now, is not eternal in its current form. It is a story written across billions upon billions of years, each chapter slower and darker than the one before. Yet even in that distant future, when galaxies fade and energy runs thin, a quiet hope lingers that intelligence, curiosity, or perhaps something we have yet to name might continue to move softly through the dark. To glimpse that future, we first have to step backward in imagination. Our present universe is still young, just under 14 billion years old, a child in cosmic terms. The stars around us are still burning brightly, turning hydrogen into heavier elements, filling the night with colour and warmth. But this age of light is temporary. In 100 billion years, most of the fuel that powers stars will be spent. The galaxies will begin to dim. The Milky Way and Andromeda will merge into a single giant elliptical galaxy, a quiet city of aging suns. The spiral arms will fade. The night sky will lose its intricate web of light. Over trillions of years, the remaining stars will grow faint and red, burning slowly like coals that refuse to go out. White dwarfs will cool into black dwarfs, dark spheres of carbon and oxygen, invisible but still massive. The universe will become a place of faint heat and memory. This is the era physicists call the degenerate age, not for moral decay, but for its quiet economy, a time when the universe runs not on radiance but on leftovers. Even in that deep night there will be motion. Gravity will continue its patient work, drawing remnants together, forming new systems out of what was once discarded. Brown dwarfs, planets, and stellar corpses will drift in slow orbits, colliding now and then in flashes of rekindled fire. Occasionally, two black dwarfs might merge, compressing what little fuel remains into a final, brief blaze. These rare sparks will be the fireworks of the far future, solitary, silent and sublime. Eventually, even these moments will end. Matter itself will begin to unravel. Protons, if they are not perfectly stable, will decay into lighter particles, dissolving the very substance of atoms. Electrons will drift away like fading memories. Black holes will remain as the last actors on the cosmic stage, swallowing what remains until they too begin to evaporate through the slow, ghostly process we call Hawking radiation. Over unimaginable eons, each black hole will shrink, growing hotter as it does, until it releases its final burst of light, a last faint exhale from the lungs of creation. And then there will be silence. No stars, no planets, no warmth, only thin radiation spreading through an ever-expanding void. Time will continue, but without change, it will lose its rhythm. The universe will have become a vast, dark sea of near-nothingness. The Black Era, the final chapter in a story that began with blinding brightness. But even here, in this seemingly absolute end, some thinkers have found a fragile thread of hope. In the late 20th century, Freeman Dyson imagined a distant civilization so advanced that it could adapt to the cooling cosmos, slowing its thought processes to match the decline of energy. Such beings would live not in seconds or hours, but in millennia between thoughts, each pause as long as entire epochs. They would survive not by defying entropy, but by learning to dance with it, stretching awareness thinner and thinner, like light fading gracefully into dusk. Later, scientists like Fred Adams and Greg Laughlin refined this vision, mapping the stages of the universe's decay and asking what intelligence might mean when the stars are gone. Their answer was both sobering and beautiful. That thought itself could persist as long as information can exist. Even in a dying universe, computation, in whatever form, could continue, provided it wastes no energy, erases no memory. This idea of reversible computation became more than an engineering goal. It became a kind of philosophy. To think gently enough is to endure. Perhaps, then, the legacy of intelligence will not be in machines or monuments, but in the discovery of how to live within the universe's fading breath. If consciousness can slow to match the rhythm of cosmic decline, if memory can survive as pattern rather than matter, then the end of stars might not mean the end of awareness. The universe could continue reflecting upon itself in quieter, longer intervals until even time itself becomes indistinguishable from thought. There's something deeply peaceful about that image. Not despair, but release. The idea that existence, like a song, can end not with a sudden stop, but with a note that lingers, reverberating softly into eternity. The cosmos began as an explosion of the light and will end as a whisper, and in between those two moments lies everything we have ever loved, known, or dreamed. The long night is not punishment or tragedy. It is simply the other side of creation. If life or intelligence endures that far, its greatest act of wisdom may be gentleness. To use energy sparingly, to waste nothing, to think in cycles instead of lines. It may learn to exist as the universe does, quietly, patiently, fully aware of its own impermanence. Perhaps this is what we are being trained for even now, to understand that the future is not guaranteed, but that meaning can outlast matter. That thought, once born, has a way of echoing beyond its source. And if, one day, the universe grows too thin even for thought, perhaps the echo will still remain, not as words or light, but as a trace of pattern in the fabric of possibility. Maybe reality will remember having been aware. Maybe, in some unknowable way, that memory will seed the next creation, the next expansion, the next beginning. In that sense, the end is never truly the end. It is simply the quiet inhalation before the next breath of being. And so, as the long night descends and the stars go out one by one, the faint hope remains that somewhere, in the dark, the universe will still be thinking, still remembering, still dreaming of itself. If we drift still further into that imagined future, past the age of fading suns and the slow evaporation of black holes, we enter a realm where the word time begins to lose meaning. And yet, in this vast hush, there is still something deeply human to wonder about. What will remain? Not of matter nor energy, but of memory. Every civilization, every life leaves traces, imprints of structure, intention, and story. Could the universe, in its long night, still hold the memory of what once was alive within it? Could consciousness, even when silence reigns, still echo somewhere in the folds of space-time? Memory is a gentle thing. It doesn't need to endure as objects or monuments. It can survive as pattern. The warmth you recall from a summer afternoon, the rhythm of a voice long gone, these live not as matter, but as organization. Information. And information, according to physics, can never be destroyed. It can only change form. It may scatter, diffuse, rearrange itself, but it persists. In that sense, the universe itself is a kind of memory, a grand archive, recording the transformations of everything it contains. Even now, the cosmic background light carries the record of the early universe. Every photon that escapes a star, every particle that shifts its energy, contributes a line to that unending script. The laws of physics ensure that this information is not erased, only written in languages we may never fully read. If, as some physicists suggest, the cosmos is holographic, then the surface of reality may already hold the sum of everything that has happened. Every thought, every action, every moment of awareness. It may all be there, woven into the quiet geometry of existence, waiting like the faint ink on an ancient manuscript. As the universe cools, that writing will fade, not in content but in clarity. Entropy, the steady diffusion of energy, will blur distinctions, mixing signals into a background hum. Yet the traces will remain, too faint for reconstruction, but real nonetheless, like the echo of a song that can still be felt even when its notes are gone. Perhaps memory too will adapt. Maybe intelligence, whatever form it takes, will learn to think not in flashes of activity, but in slow ripples of coherence, preserving meaning through sheer continuity of pattern. There is a quiet beauty in the idea that information is the most persistent substance in existence. Energy transforms, matter decays, but information, the structure behind them, may endure. Each interaction, from the collision of galaxies to the blink of an eye, alters the cosmic record in some small way. The fabric of space-time itself remembers, in its curvature and its fields, what has passed through it. To exist is to leave a signature, and in the end, perhaps that is all that eternity requires. You might think of it like footprints on a beach. The waves of time sweep in, washing away detail, softening edges, but they never quite erase the imprint completely. The sand remembers, even if no one is left to see. Likewise, the universe carries the faint relief of everything that ever was, a cosmic palimpsest where each new story overlays the one before. The ink never dries, it simply sinks deeper. For a civilization that learns to understand this, the future could become less about survival and more about participation, not fighting against the fading light, but writing gracefully into it. Imagine an intelligence so advanced that it no longer seeks to preserve its form, but its meaning. It might encode its history into stable patterns of particles, or into quantum correlations woven across light years. It might transform itself into the structure of space-time itself, thought without substance, memory without body. To such beings, existence might feel less like presence and more like resonance, a harmony between pattern and possibility. Even we, here in the early dawn of cosmic time, have already begun that work. Every message we send, every signal broadcast into space, becomes part of the universe's record. Even if no one hears it, the wavefront continues outward forever, spreading thinner and fainter, but never truly disappearing. Our songs, our mathematics, our small words of love and fear, they all become part of that grand tapestry. Somewhere, 1,000 light years away, a faint radio pulse carries the sound of our curiosity. It may one day dissolve into noise, but for a time, for a very long time, it will persist. It's humbling to realize that the universe has been keeping memories long before we learned to record our own. The light from distant galaxies reaching us tonight began its journey when multicellular life was just emerging on Earth. That light is a kind of message, written billions of years ago, still decipherable in our telescopes. We are, in some sense, the readers of the universe's autobiography, turning pages written in starlight, learning how space remembers, and perhaps memory itself is not a passive record, but a creative act. To recall something is to recreate it, to give it form again. In that way, memory is a small echo of creation, the act of bringing what once was into the present. When consciousness remembers, it momentarily reverses the flow of entropy. It pulls coherence out of chaos, form out of noise. The same might be true for the universe, that each new emergence of awareness in any era is its way of remembering itself. Life may not be an accident, but the cosmos's preferred method of recalling its own story. In the long night of the universe, then, perhaps the faint hope is not only that intelligence might survive, but that meaning might continue, not frozen, but continually renewed through new forms. The end of one civilization could become the beginning of another, the data of one mind becoming the seed of the next, information flowing endlessly forward, reweaving itself, like a melody carried through generations of instruments. The tune changes, but the music remains. If we look closely at our own moment in cosmic history, we might see that we too are part of this continuity, one verse in a song that will long outlast its singers. What we create, what we learn, what we love, it all becomes part of the pattern. Even as individuals fade, their effects ripple outward, folded into the collective memory of the world, and beyond that, into the memory of the cosmos itself. The stars are still burning now, and for billions of years more they will continue to shine. We live in an age of warmth and light, still close to the beginning, far from the quiet end, but it is worth remembering that we, who dream under these stars, are already the ancestors of that distant future. The echoes we leave, our knowledge, our kindness, our curiosity, will become the faint music that fills the long night. And maybe, just maybe, that will be enough to keep the universe dreaming a little longer. If we follow the thread of memory all the way to its edge, we find that it does not end in silence. Even when the stars have dimmed and the atoms have slowed, something endures, not as matter, not as flame, but as continuity. The universe, it seems, does not die. It changes its rhythm. It drifts from movement to stillness, from sound to echo, from brightness to the faint hum of presence. And somewhere within that endless transformation lies the same story that began at the dawn of time, energy becoming structure, structure becoming awareness, awareness reflecting upon itself. The continuum remains unbroken. When we look back across everything we've discovered, from the trembling of electrons to the birth of galaxies, a quiet pattern reveals itself. The universe has always been learning to organize itself. From chaos, it built simplicity. From simplicity, complexity. From complexity, consciousness. Each step was not forced, but invited, as if the cosmos preferred coherence to disorder, meaning to emptiness. Even entropy, that great disperser of energy, serves not as a destroyer, but as a composer, redistributing potential so that new forms can arise. Disorder is not the end of creation, but its rest, the pause between breaths. Perhaps this is why consciousness emerged at all. Life is the universe briefly pausing to notice itself. Awareness is not separate from physics. It is what happens when the laws of nature find a way to turn reflection inward. The fact that we can ponder quantum rules, trace the age of galaxies, or imagine futures beyond the death of stars means that the universe has, through us, become self-aware. Every observation, every act of wonder, completes the circle that began with the first light. The cosmos wanted to be seen, and we are the seeing. You might imagine the entire history of reality as a long, slow unfolding of thought. At first, it was the thought of existence, the simple recognition that something can be. Then came differentiation, the awareness of opposites, of light and shadow, matter and void. Later, complexity arose, the thought of pattern, of harmony, of interaction. Finally, in life and mind, the universe began to think of thinking itself. What we call progress is not a ladder of superiority, but a deepening of reflection, the cosmos recognizing more and more of its own face. This continuity does not depend on species or form. Long after humanity is gone, the pattern will remain. Somewhere new systems may arise, biological, digital, or something beyond both. They will carry forward the same essence, the impulse to know, to connect, to wonder. If intelligence is the universe's method of remembering itself, then every civilization, every consciousness, becomes a continuation of that memory. The story has no final chapter. It is written in recursion, like the ripples that continue long after the stone has sunk. Even now, in our brief epoch of the light, we are participants in that unfolding. Every experiment, every poem, every quiet act of kindness contributes to the shape of the universe's awareness. When we measure the cosmic background, we are reading its oldest memory. When we build quantum computers, we are teaching the universe new ways to process its own possibilities. When we gaze up at the stars and ask where we came from, we are echoing a question the cosmos has been asking itself since time began. We are not separate from that question. We are its voice. The continuity of being also suggests something else, that meaning does not depend on permanence. A wave that rises and falls still moves the ocean. A life that begins and ends still alters the shape of reality. To exist, even briefly, is to participate in an infinite story. We sometimes think of mortality as an ending, but perhaps it is simply a return. The merging of our individual pattern back into the large one that holds everything. In physics, nothing is ever truly lost. It only changes form. In life, the same may be true of awareness. What we call death may be another transformation, the dissolution of local memory into the universal field from which it came. This doesn't need to be a grand or mystical claim. It's a statement about continuity. Just as the atoms in your body were once forged in the hearts of stars and will one day return to space, perhaps the information carried by your mind, your experiences, your choices, your small moments of understanding, will also find new expression. It may not reassemble into a you, as you know yourself, but it will contribute to the universe's ongoing thought, its quiet evolution of meaning. Every act of perception changes the fabric of existence in some infinitesimal way, and those changes accumulate. Awareness leaves ripples that never truly fade. You could think of it as music, a symphony so vast that no single instrument can play it all. We each contribute a note, a phrase, a vibration. Some notes are brief, some endure, but together they form the melody of being. The song doesn't belong to any one of us, nor does it ever stop. It expands, modulates, weaves new harmonies into itself. When a note ends, its resonance continues in the air, blending into the next. Life, death, thought, and time, they are all parts of that same resonance. This realization transforms how we see both the universe and ourselves. Instead of asking whether we matter in the face of such immensity, we might ask how we participate. The question is not about scale, but about contribution. Not how big am I, but what note do I add to the music? A single photon travelling for billions of years can illuminate a world. A single act of compassion can alter the trajectory of countless lives. even the smallest gesture is woven into the fabric of continuity. The cosmos remembers everything that moves through it. And so, perhaps the faint hope of the long night is not just survival, but resonance, the assurance that nothing meaningful ever truly disappears. We live in a universe that is always transforming, but never forgetting. The matter that makes us, the patterns that think within us, the love that binds us, all of it becomes part of that endless reconfiguration. In this way, the end of one form is simply the prelude to another, the last note of one movement blending into the first of the next. When the final star has faded and the last atom has cooled, there will still be this, the pattern, the possibility, the quiet hum of being. The universe will continue its silent conversation with itself, not through words or light, but through the unbroken continuity of existence. And if consciousness arises again, in whatever form, it will find the same truths we have found. That to exist is to wonder, that to perceive is to create, and that even in darkness, awareness remains the faint, enduring glow that keeps the cosmos alive. And so, our story comes full circle, from quanta to consciousness, from particles to poetry. What began as a question about the smallest units of energy has unfolded into a meditation on the largest questions of meaning. Perhaps that is the ultimate symmetry of the universe, that the tiniest vibrations and the grandest thoughts belong to the same continuum. The quantum roots of reality are not beneath us, they are within us. And in the long stillness between stars, their quiet rhythm will go on,